Hey, stats people. Today we're going to formalize our four-step plan for the proportion of a significance test, or I should have said a significance test for a proportion of a population. Um, it's going to be another four-step plan, and by the time we finish this, we're going to have more than one four-step plan routines, but the basics of the four-step plan are always going to be the same. It's going to be state, plan, do, conclude. So doing those four things, if you do them and you do them right, you're going to make sure you maximize all of your points on a free response section. So let's get ourselves started. Many students claim that they can taste the different colors in Skittles, and today we're going to conduct an experiment to perform this corresponding significance test to see if students really can taste the rainbow. Now, usually we would do this in class, and the idea is you're going to pinch your nose and try a bunch of Skittles, and also blindfold yourself and try the Skittles. Now, each person in class would get 10 Skittles, and you would, take your guess about what color the Skittle is. And your table partner would help you by identifying the actual color. Of course, you wouldn't let them know until the end of the experiment. So we did this one year. We had 29 students, and we gave each student 10 Skittles. And what we found was that students correctly identified 84, the entire class, 84 Skittles were tasted correctly or correctly identified out of the 290. So we're going to go and start this four-step plan with the state section. And in the state section, there are four things you need to state. Number one, the parameter. Number two, the statistic. Number three, the hypotheses. And number four, the significance level. So let's start with the parameter. Here, we're talking about Skittles, and we're talking about a proportion. So this is the proportion of Skittles that are correctly identified. Sometimes we make a big deal about writing the true proportion every time. And that's going to be a good rule of thumb. I think I'm going to go ahead and stick with that. So P is the true proportion of correctly identified Skittles. Statistic P hat is the proportion of Skittles that were correctly identified. I have that at 84 on 290. You don't have to turn this into a decimal, but I strongly believe that if you are going to turn this into a decimal, you should put it to 4 decimal places for accuracy and for uniformity. Anytime we do a proportion in AP Stats, I try to keep it at 4 decimals. Of course, ending zeros don't really matter. You can leave or leave off zeros if you want. Okay, there's our statistic P hat, and the next is hypotheses. To delve into that, there are 5 colors in the Skittles rainbow. And if you want to prove that you can actually taste the rainbow, then you have to assume that you cannot taste the rainbow. So we have to assume the opposite of what it is we're trying to prove. And if you really can't taste a rainbow, that means you're just guessing. And if you're just guessing, then if there are 5 colors, then you should be correct about 1/5 of the time. Which means that we should make our H naught P is equal to 0.2. Now, if you can taste the rainbow, that means the proportion should be greater than 0.2, meaning you make more guesses than just guessing. So, H alternative then, well, H alternative is going to be P is greater than 0.2. Now, for the significance level, nothing really has been specified. So if that happens, then you're always going to say that the alpha is going to be 0.05. Now, remember, we choose alpha equals 0.05 because it's kind of a balance between a type 1 error and a type 2 error. Because if you make your alpha equal 0.01, 1%, that means that you're probably not going to make a type 1 error, but you're more likely to make a type 2 error. And if you go to 10% with that significance level, that means that you're more likely to make a type 1 error, because alpha is 0.1, and you're less likely to make a type 2 error. So significance level of 5% is the balance between the two. Next, we're going to name our procedure, and we're only going to take one sample. Even though every student in the classroom partook of 10 Skittles, we're combining it to create one really big sample. So this is going to be a one sample. Since we're dealing with proportions, proportions is always going to be a z-interval. And in this case, instead of an interval, it's going to be a z-test. So we'll highlight that z-test here just to signify to you that that is where the difference is between this and the confidence interval. Instead of a z-interval, we're going to do a z-test. So for checking conditions, there are those same three conditions. First, there's a random condition. There's also the 10% condition. And then there's the normal condition. So let's start with random. Was this a random sample? Well, I don't know how you feel about it, but when we do this in class, we have the students randomly select their Skittles. So I think that's going to be good enough for us to say that the samples were randomly selected. One year we even did blindfolds, so yeah, sure. If it's a blindfold selection, then that's a random selection. What about the 10% condition? Were we sure that we sampled less than 10% of all Skittles? Well, Skittles have been in production for quite a while. There are, we only sampled 290 Skittles. 10 times 290 is 2,900. I'm pretty sure there are more than 2,900 Skittles in production worldwide. So we can say that 290 is less than all Skittles produced. Finally, for the normal condition, the correct one to use for proportions is large counts. Whenever we do anything with proportions, we're always looking at large counts for the normal. So we have NP is 84. Remember that you can shortcut your mathematics because 84 is a number of correct guesses. So the number of successes is always the same thing as NP. So 84 is definitely greater than or equal to 10. And then N1 minus P is just the number of failures. So if there were 84 successes and there were 206 incorrect guesses, and that's also greater than or equal to 10. So all the conditions have been checked, and we're ready to go to the do part. So we're on do, and we're going to figure out the general formula. For any hypothesis test, the test statistic is going to be statistic minus null over the standard error. The specific formula for not a confidence interval, a hypothesis test for a proportion is p hat minus p square root p 1 minus p over n. And remember, you want to memorize that a little bit at a time. You want to memorize that the mu of p hat is p, which you should have memorized basically in chapter, I think, 7. And also you want to memorize that the standard deviation for p hat, sigma p hat, is square root of p 1 minus p over n. Again, that should have been memorized all the way back in chapter 7. Here you can just put it all together and, you have all the little pieces, just got to put it together now. Now, for the work, you need to substitute all of the values first. So just substitute the numbers first and then go right to the answer. Once you have your z-score, you're going to do the picture of the normal curve. You're going to label it with the appropriate mean and standard deviation. Locate the z. So in our case, it's 3.8. That's really far off to the end, isn't it? We're going to put in our test statistic at the bottom and our z-score at the top, 3.819. Let me rephrase that. We're going to put the test statistic 3.819 above the curve. We're going to put our statistic underneath the curve, 0.2897, and you'll notice that as far away as we are from the mean, there's pretty much no area to be had. So ordinarily we would shade in, and I think I'm just going to shade in a little piece red right now, just to appease whomever. So there's our picture of our normal curve. Don't neglect that, because a lot of the AP readers say that they really want that curve. It tells them that the student understands the connection between the normal curve and the test. Reading through what I have here, the next thing says test statistic, but we've already done our test statistic, so there's no need for us to do that. Maybe I'll just move it over to the other side here where it says test statistic. And lastly, p-value. And one of the things I forgot to mention was that, you will notice that I shaded to the right of 3.819. And the reason we did that was because our alternative hypothesis was p is greater than 0.2. So if we have greater than 0.2 for the alternative hypothesis, we shade above the test statistic, which leads us to our p-value. The p-value is z greater than 3.819. Again, that greater than is the same inequality sign that is used in the alternative hypothesis. Whoa. I've gone ahead and I've kind of shoved everything over just to make room. But we got the p-value then is equal to the probability that z is greater than 3.819. On the calculator, you're going to do a normal CDF with the low of 3.819, the high of infinity, and mu is 0 and sigma is 1. Now this time, I think in previous chapters and sections here, I used the, not the test statistic, but the actual statistic, and I've kept the mean and the standard deviation. You could do either. It should give you results that are similar. And whatever you do, just make sure you notate exactly what you put in your calculator, especially if it's going to be different like we did. Anyways, I say that the answer here is 0, but that's not actually what I got in my calculator. What I actually got was 6.702 and then E -5. So you want to be careful about what you write down. A lot of students who are not paying attention will actually write down 6.702 and leave it at 6.702, which doesn't make sense, because how can a probability be 6? We already learned that that's not true. So be careful, be on the lookout, and the thing you're looking out for is E -5 at the very end of your calculator. That is scientific notation. That's the same thing as times 10 to the -5. That's the same thing as 6.702 times 10 to the -5th power. And as long as that power is -4 or -5, -6, -7, technically smaller, but most students would say bigger. But as long as it is a negative number that's greater than 4, that's going to be equal to 0 for you. So anything to the -5 power, that's 0. Finally, we're going to make a conclusion here, and you just need to copy and paste the sentence frame. Okay, since the p-value is, well, let's check. Alpha was 0.05. 0 is less than 0.05, so definitely less than alpha. So if the p-value is less than alpha, that means we support the alternative hypothesis. So the true proportion of correctly identified skittles is greater than 0.2. Now, there's something I kind of want to mention to you, is where did that phrase come from? And if I scroll up over here, what I see here is I defined P to be the true proportion of correctly identified skittles. And that's the exact same phrase that I'm going to use down here with my alternative hypothesis. The true proportion of correctly identified skittles. greater than 0.02, that comes from the alternative hypothesis. So all of that in the state section comes together to create the alternative hypothesis, in words. And then the next thing over here is going to be that, if you want, you could interpret what this means. And just kind of cutely, I'm writing, this means that students can taste the rainbow. So that takes care of our hypothesis test. We've got the 4 parts: state, plan, do, and conclude. Very similar to what we did for our confidence intervals. So we're ready for our important ideas here. First thing we have is our 4-step plan: state, plan, do, and conclude. There are a few different differences between this and the confidence interval. So make sure you note where those are. And Learning Target 2 is a 2-sided test. And this occurs if the alternative hypothesis is of the not equal variety. So when this happens, you're going to take the p-value and you're just going to multiply it by 2. And we'll show you why we do that in the Check Your Understanding. I'm seeing that this is going to be a not equal to alternative hypothesis. So let's go ahead and take a look at our Check Your Understanding. Actually, maybe we should pause here for a couple seconds, get a good look at the important ideas, and then let's go to Check Your Understanding. According to the National Institute for Occupational Safety and Health, job stress poses a major threat to the health of workers. A news report claims that 75% of restaurant employees feel that work stress has a negative impact on their personal lives. I just read that statement, and that 75%, because it said a news report claims, that's saying to me that my null value is going to be 0.75. Managers of a large restaurant chain, they wonder if that claim is valid for their employees. A random sample of 100 employees find that 68 answer yes when asked, does work stress have a negative impact on your personal life? So, do these data provide convincing evidence at the alpha equals 10% level that the proportion of employees in this chain who would say yes differs from 0.75? So just to make sure that we're all kind of interpreting this the same way, we know that the sample of 100 said 0.68, but that does not ensure that the entire, all of the employees have that same proportion of 0.68. That was just because we were looking at a specific set of 100. To test whether or not all employees would say yes, we're going to check and see if, based on sampling variability, 0.75 is not an option, or is an option. Where does 0.75 lie because of sampling variability? So we're going to start with the parameter. What is our parameter? We're going to say that P is a true proportion of employees who say that stress has a negative effect. Notice that I've gone ahead and italicized true proportion. Make sure you're writing true proportion as well. The hypothesis here is H naught P is equal to 0.75. 0.75 being that parameter value, that null value that we identified earlier. The statistic is p hat equals 0.68, which is a number that came out of the experiment or the survey. The random sample is 68 out of 100, and that's where that 0.68 comes from. The p hat always comes from either the experiment or the survey. Okay. And we just read that the significance level is 0.1, so that's usually not a difficult part here. So we're ready to name the procedure. So we're going to name the procedure Bobby. Just kidding, it's a one sample Z interval for P. The 3 conditions we need to check for every one of these hypotheses tests are going to be random 10% and normal. Let's go one by one. For the random, I see in the problem that we have a random sample. So for random, I'll write something like the 100 employees comprise a random sample. Now for the 10% condition, this is where we get a little bit of iffiness, because there are 100 employees in the sample, and that needs to be less than 1/10 of all employees, meaning there has to be more than 1,000 employees. Now, I think I remember reading that this was a large restaurant chain. Yes, this was a large restaurant chain. So that kind of leads me to believe that there is very likely more than 1,000 employees. So to qualify the 10% condition, I'm going to say, quote, large restaurant chain, likely that 100 is less than 0.1 n, or 0.10 times n. So for the normal condition, we have to do large counts. Anytime we deal with proportions, it's going to be large counts for the normal condition. NP is equal to 68, which is greater than equal to 10. Again, I didn't do any math. I just counted how many successes in the survey. And if there were 68 successes, that means there were 32 failures, and 32 is also greater than equal to 10. So the conditions all check out. We're ready to do our general formula. General formula test statistic is statistic minus null over standard error. The specific formula here is z equals p hat minus p over root p 1 minus p over n. Don't forget that the entire denominator is in parentheses, or the entire denominator is inside the square root. For the work, we're going to substitute in the values. Don't forget that you need to use p inside of the standard error and not p hat. That's a common mistake. Okay, so for the test statistic, I get negative 1.617. So let's take a look at the picture then. For the picture, we've got ourselves a pretty normal curve, and we're going to start labeling it. Now on our curve, we're going to mark that 0.68 and correspond it to that negative 1.617, and we're going to shade to the left of it because, of course, it is the tail that we are interested in. And that looks pretty good, but remember what we said earlier. We have over here the alternative hypothesis is p is not equal to 0.75. That tells me that we have a two-tailed test. Well, we already have found the area of one tail. So when we go back to our picture, we've got to find the area of the other tail. So the idea here is that we don't care if we are different. It said differs from 0.68. And we don't care if that difference is because it's too big or if it's too small. So whenever you see something like differs or is different from, it doesn't really give an indication to smaller than or bigger than. That's when we have to implement our two-tailed test. So that's how our picture differs. This brings us down to our p-value now that we've got our picture. Not a whole lot about this is different, except for when you're doing the p-value, you find the area of one tail. Here I'm finding the area of the right tail, the one in red, and then you multiply it by 2. That'll give you the area of both the red tail and the green tail, because the two tails have the same area because of the symmetry of the normal curve. And we see that that p-value is quite large. Definitely it's larger than our alpha. And then conclusion-wise, since the p-value is greater than alpha, the data does not support that the true proportion of employees who say stress has a negative effect differs from 0.75. And finally, for question 2, we've got a 90% confidence interval for the Restaurant worker data was also created and found to be 0.60 to 0.756. So explain how this confidence interval is consistent with, but gives more information than the test. Okay, well, the one thing I want to notice first is the significance level was 0.1 and the confidence level is 0.9. So when that happens, the confidence interval and the alpha level, when they're equal to 1, when you add them and you get 1, that means they're going to be consistent with each other. Or the two-tail test, I should say. The two-tail test alpha is 0.1, and then the confidence interval is 0.9. That means that the two-tail test and the confidence interval are complements of each other, I should say. So we take a look at our values, and we see that we have 0.75 is inside this confidence interval. So we're saying that since 0.75 is inside the confidence interval, is between 0.603 and 0.757, 75% is a plausible value for the true proportion. So the confidence interval says that the true proportion of employees who say that stress blah 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 blah, it could be 0.75. In other words, it's not different. We have no evidence that it's different than 7.75. The true value is somewhere between 60.3% and 75.7%. So that's our work for today. Good luck there with your 4-part plans and your confidence intervals for a proportion. And I'll see you next time here when we start looking at the mean.